Hi, this is the second example problem video. Here we're going to cover examples 3.6 and example 3.7 that have to do with torsional shear stresses. Okay, so first of all, we're going to compute the maximum torsional shear stress in a shaft having a diameter of 10 millimeters when it carries a torque of 4.10 Newton meters. So the given is our shaft of 10 millimeters in diameter and our torque of 4.1 Newton meters, and we are to find the maximum torsional shear stress. So this is our equation. Tau max equals, it's actually TR over J, because the maximum shear is always going to be at the outer radius, because at the center of the shaft, the torsional shear is 0, but as you get out to the outer radius, that's where you're going to find the maximum torsional stress. So when they're asking for the maximum torsional shear stress, you always have to go to the radius R. That's where you're going to find the maximum shear. Then we're going to go to Appendix A, Appendix 1, and find our polar moment of inertia equation, which is pi d4 over 32. And that calculates to 982 millimeters to the fourth. Now again, I'm going to work in millimeters. I think this just works out the best. Okay, so when I'm substituting into this equation here, C is going to be R, which is d over 2, which is 5 millimeters, and then here's J. Go into the equation, write your units out. Write your units out when you do this, because that way you can actually see if you got everything correct. Okay, so when I put in my torque, I've got newtons and meters. When I put in my radius here, I've got millimeters. And then when I put in my J, my polar moment of inertia, I got millimeters to the fourth. Okay, so the only thing that's odd up here is I have these meters and I have millimeters. So I'm going to put in this factor here that converts this unit of meters into millimeters. Okay, so there's 10 to the third millimeters per meter. And that gives me 20.9 Newton millimeters squared. Now, as I discussed in the lesson before, we have an identity that says, hey, 1 Newton millimeter squared equals 1 MPa. That is a very handy relationship. We're going to use it here. And really, that relationship allows us to work in millimeters pretty much unabashed, okay? So once we get our answer in Newton millimeters squared, we can convert that handily to MPa. So our answer is 20.9 megapascals. Now, problem 3.7 continues with the same problem, but what we're doing here is we are looking at the angle of twist. Okay, so let me bring this graphics down here. Compute the angle of twist of a 10 millimeter diameter shaft carrying 4.1. So this is the same problem as before, with the shaft being 250 millimeters long, and the steel has an 80 gigapascal modulus of rigidity, or shear modulus. Express the result in both radians and degrees. So the given here, we have our shaft of 10 millimeters in diameter. We have the torque of 4.10 Newton meters. We have a length of 250 millimeters, and we have a modulus of rigidity, or shear modulus, of 80 gigapascals, with the polar moment of inertia from the previous problem of 9.82 millimeters to the fourth. And what we're going to find is the twist in degrees, and we're also finding the twist in radians. Actually, we're going to find the twist in radians first, because that's what our equation 3.11 is going to give us, and then we're going to convert that radians into degrees. So let's work the problem now. Okay, so here's our gigapascals. We're going to put that in as Newton millimeters squared. Okay, so what we're going to do is convert these meters squared here into millimeters squared. Okay, so essentially what we got is 80 times 10 to the 9th divided by 10 to the 6th, which gives us 80 times 10 to the 3rd Newton meter millimeters squared. We're going to substitute that into equation 311, where our theta equals torque times the length divided by the modulus of rigidity divided by the polar moment of inertia. Okay, so I set all my values in here. Remember to write down your units because it's very important. So what you're going to find here is that these newtons divide out these newtons here, these millimeters squared divide out these millimeters squared. So really what you're going to end up with is, essentially nothing, no units whatsoever here, and no units whatsoever is radians. Okay, radians is a dimensionless quantity. So what we end up with is 0.13 radians. Now, how do we convert radians into degrees? Okay, we have a identity factor here where 360 degrees equals 2 pi radians. So 2 pi radians is the circumference of a circle. All 360 degrees is also the circumference of a circle. So we're going to take our radians times 360 degrees divided by 2 pi radians, and then we get 0.75 degrees. Okay, that's the problem solutions. For your homework, I gave you something that has a concurrent force system. 3.9, if you will, is one of our force problems. It's a concurrent force system from, that's what you talked about in either statics and strength of materials or advanced strength of materials, this concurrent force system. Please don't let this confuse you. You need to draw a free body diagram at this point right here, and then you're essentially going to have two equations and two unknowns. You're going to have the tension in the rods. You're going to have forces in the x direction equals 0 and forces in the y direction equals 0. You're going to have two equations, two unknowns, and then you should be able to find for what the tension is in the rods. Once you find the tensions in the rods, well, that's that part of the problem. And then you had another problem too that talks about compute the shear stresses in the pins. Okay, so what goes on with this one is you have pins at each one of these three joints. Okay, and what we're asking for is what is the shear stress in these pins at these three joints. Now, the first thing you need to do is to calculate the load in the rods. That was 3.9. And then the next thing you need to do is calculate the shear stress in the pins. I want you to assume for me how the arrangement's set up. I mean, if you're going to assume that this pin here is set up as single shear, yeah, write that down in your solution. These pins are in single shear, and if this one's in double shear, mark it down. This pin is in double shear, so that way we can validate our assumptions when we answer our problems. Okay, so I just didn't want that one to throw you for a loop. That's it for our video presentation for the example problems. Good luck on your homework. Thank you.